Hello and welcome to a new video. My name is Herwig Juster and today we discuss how injection molding processing conditions are impacting crystallinity and as a consequence the performance of plastic parts. Okay, let us get started. So in general we start with the mechanism of crystallinity, and crystallinity only plays a role in semi-crystalline polymers such as the polyamides and polyolefins. For example, high-density polyethylene can achieve crystallinity levels of up to 85%, and a high-density polyethylene ranges also among the polymers with the highest crystallinity. Although for most semi-crystalline polymers, crystallinity ranges below 50%. So this is a rule of thumb. And so what are the main drivers for crystallinity? It's time and temperature. So formation of crystallinity starts below the melting point and stops below the glass transition area. So this is the range. And as long as the material is above the glass transition point, the molecules are mobile, so the mobility is given to form regions of crystallinity within the amorphous region, because we have amorphous and the crystal regions. So as a consequence, the most effective temperature window is below the melting point and above the glass transition point. And however, we have to keep in mind crystal formation and growth varies for each semi-crystalline polymer, and for also this really is depending on the supplier of the material, of the manufacturer, so it's really different growth rate. And there is an optimum temperature for growth, and this is to find out this optimum temperature. The slowest growth is achieved just below the melting point. This is also clear, so we have to move more towards the glass transition point. So now it's important what to take care during processing, so injection molding. In general, the faster the crystals form, and with them the material modulus, the faster the part can be demolded. And when you look for optimizing the cycle time, certain molders tend to lower the mold temperature to have a colder temperature. However, this is in fact counterproductive. So selecting the optimal mold temperature will result in a high yield quality part. And here I have a table which shows the crystallinity of selected polymers with their tool temperatures. So we have here a POM, so polyacetals with over 90% crystallinity and mold temperatures between 40 to 90, and there is again this range, and to find the optimum we have the most growth. So HDP, as we already discussed, 85%, really high. Also a PA46 is around 80%, really high. You see here already the mold temperatures between 60 and 120. Then we have semi-aromatic polyamides, 66i with 60%, PPS around 55, PA66 you can say it's around 50, and the peak around 40% crystallinity. And you see with peak we have already really high, almost 200 degree in mold temperature. Okay, so what are now the advantages of the high crystallinity? So on the one hand, we already discussed the better the crystals form, the faster I have a modulus and can start the demolding. And high crystallinity also results in high strength, stiffness, higher chemical resistance, and higher resistance towards environmental stress cracking. So ESC, we'll also make a video on ESC later. Furthermore, the modulus of retention of unfilled semicrystalline polymers above the glass transition is higher compared to amorphous polymers, and this is a result of the crystals. For example, when you take an unreinforced PPT, polyester, it has a modulus at room temperature of 2.3 gigapascal, and at 100 degrees C we still have levels of 330 around megapascal. And when you think of polyamides, there we have always the water uptake issue, and which mainly occurs in the amorphous region. So when it is possible to achieve high crystallinity, the lower are the amorphous regions, which lowers then the possibilities to take the water up. And as a result, the part dimensions will be kept more accurate. Okay, so to summarize and to conclude, when you think polymers such as polyethylene with a glass transition below room temperature can handle colder mold temperatures better than engineering polymers, which have the glass transition above room temperature. And so in this case, cold mold temperature will result in lower crystallinity and problems with part performance. So you have to find the optimum crystallinity temperature between above TG and below the melting to have a good molding process itself, and then also a part performance. And if you want to find more about polymer engineering topics, I highly recommend you my blog, find out about plastics.com, as well as my online courses on polymer material selection. I will link you both the blog and the online courses in the description below. Okay, so which video to watch next? Here in this video we discuss how to calculate the residence time in polymer injection molding using an online tool. Thank you for watching, and do not forget to subscribe and smash that like button. Till next time, bye!